Greetings from Denmark. I'm Rafiqul Gani. It's a pleasure for me to give this lecture at the AVEVA PROII Simulation Advisory Group meeting. I also thank John Hernandez for inviting me to give this lecture. Let me first share my screen and get it started. And okay, so I'm based in Denmark, and my co-authors, Chakrapat, Nichakon, and Orakoch are working in the Thai office of PSC for Speed Company. I spent some time in Thailand and also time in Denmark, but for the last 16 months, because of the COVID, I've been in Denmark all the time. So this talk is about the use of PROII and different options within PROII for simultaneous design optimization, heat integration, and also another example of simulation of dividing wall columns. So let me start on the first topic, that is simultaneous simulation, design optimization, and heat integration. I will introduce the concept first. So the base case design, or the starting point, is that we have a base case design of a chemical process, as you see from a simple diagram. What we need to do is to convert this process design into a process simulation, and then verify that the design is as simulated is correct. And then we will perform economic analysis and analysis of hotspots, meaning where are the problems that in the design that uses more energy, for example, than necessary. And based on that, we will define some targets for improvement. And these targets for improvement will then be used to define the optimization problem, where starting with the optimizer will give some values, initial values for selected design variables, which will then be passed into PROII. PROII will do the simulation and pass back to the optimizer all the stream values and all the process values. Using these values, the optimizer will calculate the objective function, in this case to maximize the profit, for example. And in the objective function, which you might not be able to see it, I will push it upwards, okay. That the objective function has the revenue from sale of the product, operating cost, and also the utility cost. Now, the utility cost cannot be calculated directly from the stream values by the optimizer. We need another additional tool. That is, if we know all the flow rates, the temperatures, the energies, then through heat integration, that is a utility tool, it will tell us what is the minimum utility required. There are different options to do it. The most common option is a pinch analysis. That is a graphical technique where the hot streams and the cold streams are integrated in such a way to find out what is the additional cooling and heating needed. As we all know that this gives us a lower value of the additional heating and cooling needed, but not necessarily the optimal values. To get an optimal value, we need to formulate what is known as a transshipment model, where you see on the figure on the left, if we have two hot streams and that needs to be cooled, and two cold streams that needs to be heated, and the temperatures of the hot and cold streams are arranged into 4 intervals, 1, 2, 3, 4. The energy from the hot streams are given to the intervals, and the energies from the intervals are distributed to the cold streams. And then, so we can say that the hot streams are the source of energy and the cold streams are the sink of energy. And if we make energy balance around each of the intervals, we will get the 4 equations that you see in the middle. And if we add an objective function, which will be to minimize the amount of hot utility, that is QS, and the cold utility, that is the cooling water needed, then we have a optimization problem to solve. This is a linear model in terms of the equations, and therefore it's a linear programming optimization. Solving this optimization problem gives us the minimum QS and CW together with the location of the pinch point, which is given, identified, where from the values of R1, R2, R3, if any of them is 0. R1, R2, R3 in principle have to be 0 or greater than 0. If any of them are 0, that is the location of the pinch point. So now what we can see is that for every iteration of the optimizer, when D is changed, the process simulator will generate new values, and the new values may change the flow rate, the temperature, the energy of each of the streams. And then it will require the solution of the heat integration. And it is not that convenient, although it can be done. And in most cases, it is done sequentially, that you simulate, optimize, and then use the optimized values to do the heat integration. But can we put this in a more systematic and efficient way? And that would be that we add the transshipment model to the calculator. So every time the optimizer needs to calculate the objective function, it has already the values of from the simulator that it needs for the flow rate, temperature, energy, and other variables that may be needed. So it can actually solve the transshipment model and pass on the utility values into the objective function. And this can be done through a user module in Pro2. And this is what I will highlight in my presentation. The ideas of this is not actually my ideas. It was given by and developed by Professor Ignacio Grossman at Carnegie Mellon University. So in the next slides, I will show through an example process design problem. Step 1, that is simulation of the initial design. Step 2, optimization of the process based on identifying some targets for improvement. Step 3, a sequential heat integration and optimization. Step 4, simultaneous optimization and heat integration. And step 5, validation. The cumin process is chosen for this demonstration, not really demonstration, illustration of the concept. So the cumin is obtained by conversion of benzene and propylene in a 2-reactor process. In the first reactor, benzene and propylene react to give cumin. Cumin then reacts with propylene to give isopropyl benzene, diisopropyl benzene. So in a second reactor, the diisopropyl benzene is converted together with additional benzene is converted to cumin. So we have 2 reactors, and the details of this process is obtained from the cited reference. So we have taken all their data. We have not changed anything, but afterwards I will discuss some changes. So based on this information and the feed information, we have simulated the process in Pro2. And you can see all the highlighted text indicate all the specifications that were given in the cited literature. Some information that were not given, we had to play with them to find out what would be the values for them in order to match all the remaining variables that the paper had given. And we have added a calculator here to calculate the objective function for us. In addition to the objective function, it is also going to calculate the carbon footprint and other information that we would like for each of the alternatives. So this is the process. The next step is that we will identify where the hotspots are, And one of the simple ways we do it, and I'm not showing everything in here, just one item, that we list all the unit operations that use utilities, hot or cold. And then we have listed them, which is, you can see on the table. And the distillation column 2 is identified to use the highest amount of cooling and heating. So this, in principle, could be a target for optimization. If we keep everything else the same, and we want to get exactly the same product, the same purity, flow rate, everything, what should be, for example, the feed location that will give us the same thing. And at the same time, minimizing the duties. We could also put column 3 for the similar optimization. And there are other points also where we could add additional optimization. Just for conceptual purposes, we are keeping the optimization problem simple. So we are just doing this one simple optimization. So in order to do the optimization, we add the optimizer available in Pro 2. We say that we want to optimize this feed location, keeping the same product specification. So all the other points are not changed, only this one is changed. And doing that, we can see that our objective function now has the profit compared to before of 9,976. It has increased to 10,361. So now with this optimal solution, we can take the hot streams, identify the hot streams and cold streams that can be integrated to save further energy and utility cost. So we find out that there is a stream going into the reactor 2 that needs to be heated. And then there is a stream that is the red stream, and there is a stream coming out of the first reactor, the cumin reactor, that needs to be cooled. So if we say that this hot stream and these cold streams could be integrated, again, just keeping the problem simple and not adding more hot and cold streams to illustrate the concept, we can do the integration. And this is the integration that is done. One heat exchanger doing the hot and the cold stream and the additional cooling that is needed. And with that, we improve the profit and we come to 10,415. So this is sequential. Now we can try to see if we do the simultaneous, what will happen. To do the simultaneous, we will have to add the heat integration module as a user module and connect it to the optimizer in Pro 2. So this is what we do. That's the user module. The stream that is going into the user module passes all the information needed of the flow rates, the temperature, the pressure, the enthalpies, and all other information needed by it to formulate the transshipment problem and solve it. And then it passes the solution into the optimizer. And doing this, we can see that we have increased slightly the objective function, the profit. That is because in this case, since we only optimize the distillation column, the temperature flow rates of the hot stream and cold stream did not change very much. And therefore, the objective function did not increase very much. However, we could have taken, for example, that we will pass less of the benzene to the first reactor and more to the second reactor. That would change things. We would also consider changing the conversion of the diisopropyl benzene in the second reactor, or maybe even say that benzene should not go out and we should have excess diisopropyl benzene. Then we will have some byproduct and the byproduct will go out at the bottom. So all of these we can add and then the objective function will be more complex, and it will change also the conditions for the hot and cold streams. But the simple design values are validated. As you can see here, now we do not need the heat integration module, and we do not need the optimizer. We just do the validation by simulation. So as summary, we can see that for the cumin production case, if you want to compare, take the case 1 and the value in yellow in profit. Also look at the carbon footprint. That first we had an initial design and a profit, but case 2 and 3 increases the profit through optimization and heat integration. And then by simultaneous, in this case, in the simple case of optimization, we did not increase very much. But if we take the other variables, like the split fraction for benzene, the optimization of the conversion, not the optimization, but slightly lower conversion than 100%, having excess diisopropyl benzene as a byproduct, and also improving the environmental aspect by not releasing any benzene, we can get to up to 10% improvement by doing the simultaneous. So that's a very good way of achieving, in this case, not only a better solution, but also improving the environmental impact, but by not releasing benzene. We have also done other processes, studied other processes like the well-known HDA process, hydrodealkylation of toluene to benzene. And compared to the published literature value, we have improved that process by about 25%. Also, we have taken simulation files from Pro2 example files, like simple methanol plant. We have improved 24% of the efficiency of energy utility reduction and or increase of profit. Cryogenic plant, 11%. A cyclohexane plant, 12%. We are also finalizing the details of VCM and ammonia plants. I don't have the values in here, so I cannot show you now. So it is possible, and it's simple and easy. All one needs is to put the heat integration module as a mathematical transshipment modules, which is a linear programming problem, into the optimizer. Now I go to the second example, which is a separation of multi-component mixtures and whether a dividing wall column could be used and what are the benefits. So we have a multi-component mixture, hydrocarbon mixture that I've used as an example. The conditions are given. If we want to do a simple kind of synthesis to find out how many different ways can we do this separation to get pure products, 5 pure products. To get 5 pure products, we need minimum 4 separation steps. And this is a superstructure which is shown on the right. It does not include just distillation columns, but also other separation techniques. And if we try to enumerate feasible separation paths for this, we will get about 184 separation schemes. One of them involving only distillation is the one that you see here, simulated with Pro2 and optimized with respect to the cost. And it turns out that if we first take out ethane, then propane, then at the bottom on the third column, the C5, and the last column C4s, that is the best sequence for simple conventional distillation columns. So the most difficult separation last, the easiest separation first. Those kind of rules can be applied here also, but it also shows the thermodynamic background, because the easiest separation is where the driving force is the highest, which is the first column. And the last column, the driving force is the lowest, which is the last column. So now with this, we will see whether using a DWC is an interesting option or not. So our original optimal flow sheet for purposes of comparison, dividing wall column is shown here, that there is a prefractionator and a dividing wall column, and then the main column. And the connection between the prefractionator and the main column is that some of the liquid from the main column is split and sent to the prefractionator, and from the bottom some of the vapor is also split and goes into the prefractionator. So the prefractionator in this way does not need a reboiler and a condenser. This kind of columns can be simulated by the well-known Petliuk column, where the prefractionator you can see on one side and the main column. The important issues here are what is the liquid split, what is the vapor split, and if we can find those values, will it always give us a better reduced energy in all cases? We can see that afterwards. But first we can see how many ways can we put this dividing wall column into the process flow sheet that we have on the right. So we can, if we want to combine two columns, it has to be two adjacent columns, not 1 and 3. It has to be 2, 3, or 1, 2, or 3, 4, like that. So we have the first two columns in the middle, 3, 4, or we can have the first two, or we can have the last two, or we can have two dividing wall columns. We can also have something called a Kybel column, which has 4 products. That is an extension of the Petliuk column, but let's keep it to the Petliuk column. So we can have 1 Petliuk column or 2 Petliuk column for this. So which is the best? Before I go into that, let me tell you about the Pro2 example file that we have created. This, the green box is the 2-column system. The first column has no specification, only the number of stages. The vapor that comes in at the bottom and the liquid that comes in at the bottom, they come at the top and bottom stages, and the vapor leaving the top leaves at the top and liquid leaves at the bottom. So there's no product specification there, only the feed location needs to be given. For the second column, there is feed specification needs to be given. That is the liquid and vapor coming into the second column. And there are 3 products going out. We give the specification of the 3 products, and we give also the recycle, that is the vapor split and the liquid split. So we specify these under the product specification. The first 3 are the specification of at the top, bottom, and middle products. We say what is the recovery. That is recovery, for example, of ethane at the top compared to ethane in the feed. And this is a better way to give the specification, because it doesn't need to match a flow rate or a composition. It just needs to match a relative value. For the simulator, it's an easier way to achieve convergence. The last 2 specifications, that is 4 and 5 that you see, are initial estimates for what should be the vapor split from column 2 to column 1, and what should be the liquid split from column 2 to column 1. And what we do is that it has to not only converge from the iteration, but we would like to optimize it. So we add an optimizer, and the optimizer then minimizes the duties in the second column, that is the condenser duty and the reboiler duty, and finds out what should be the optimal values for these 2. So when they converge, we have the convergence of the TO stream and the optimization. The additional things of membranes and component splitters that you see are adjustments that we can do to further improve the process in terms of energy, but I will not go into those details now. So this module, we can add in any process flow sheet where we want to replace 2 columns with 1. So that's one way. So we can always add things before it and always add things after it. It's not very easy to converge because the iterations for the optimization of those 2-tier streams can take a lot of time. But if we start with that, the first column always has enough liquid and vapor, then it will never break down. And if it does not break down, ultimately column 2 will converge. So it's not a problem. So what is the best sequence? This actually happens to be the best sequence of all the different sequences we have looked at. That is, convert the first 2 columns into a DWC, and any other combinations will give lower energy reduction. But this one, compared to the original, reduces the energy demand by 45%. Some combination rules: if we have ternary mixtures, we can use a dividing wall column as long as we have a non-isotropic mixture and we want 2 pure products, preferably A and C, not B. And assuming that A, B, C are in order of increasing boiling point. So A is the lowest boiling and C is the highest boiling. If we have quaternary, we can make different arrangements. So we can first use a conventional column and then a DWC. And with the conventional, we can separate A first or D first, or we can have a DWC first and then a post column separation. So the chemicals that are listed in red are the ones that will not be pure. The other ones will be more pure. So that's the second example, very short. In summary, I would say that I've shown the application options within Pro2 to perform simultaneous design optimization and heat integration. And larger benefits can be seen if the design optimization problem changes the condition of the streams used in heat integration. So formulating the optimization problem is quite important. Simulation of dividing wall columns is highlighted through a Petlick column configuration within Pro2. Application of the scheme can give good energy reductions possibilities for carefully selected mixtures to be separated. And then what I mean by carefully selected mixtures to be separated, one can see the table on the right that most of the energy intensive processes are those, or distillation column separations, are those that involve hydrocarbons. So those hydrocarbons, because of the volume of separation, because of the conditions of separation, they use more energy than what I would say the difficult separations involving water and some organic solvents and others. They are difficult, but they're not necessarily energy intensive. So if we want to make an impact, we should concentrate maybe on those distillation columns which involve a larger amount of energy. Also, for those who are interested in my presentation, you can get a copy of my slides from the host. And in these slides, I've also added additional slides after this slide, where I've given more details as appendix to the transshipment problem, to the details of the Q-min process, to the details of the design, and so on. Thank you very much. And with this, I will end my lecture.